Meter. Pmmc instrument on AC. As discussed earlier, the Pmmc instrument is polarized, that is, its terminals are identified as plus and it must be connected correctly for positive, on-scale, deflection to occur. When an alternating current with a very low frequency is passed through a Pmmc instrument, the pointer tends to follow the instantaneous level of the AC. As the current grows positively, the pointer deflection increases to a maximum at the peak of the AC. Then as the instantaneous current level fails, the pointer deflection decreases toward. When the AC goes negative, the pointer is deflected, off scale, to the left of zero. This kind C pointer movement can occur only with AC having a frequency of perhaps 0.1 Hz or lower. With the normal 60 Hz or higher supply frequencies, the damping mechanism of the instrument and the inertia of the meter movement prevent the pointer from following the changing instantaneous levels. Instead, the instrument pointer settles at the AVR-SEC 3 to 5 rectifier voltmeter 51H value of the current flowing through the moving coil. The average value of purely series S0. Therefore, a Pmmc instrument connected directly to measure 60 Hz AC indicates 0. It is important to note that although a Pmmc instrument connected to an AC supply may be indicating 0, there can actually be a very large RMS current flow in INITS coils. Full wave rectifier voltmeter. Rectifier instruments use silicon or germanium diodes to convert alternating current to a series of unidirectional current pulses, which produce positive deflection when passed through a Pmmc instrument. The full-wave bridge rectifier circuit in Figure 3 to 17 passes the positive half cycles of the sinusoidal input waveform and inverts the negative half cycles. When the input is positive, diodes D and D conduct, causing current to flow through the meter from top to bottom, as shown. When the input goes negative, D and D3 conduct, and current again flows through the meter from the positive terminal to the negative terminal. The resulting current waveform is a series of positive half cycles without any intervening spaces, see Figure 3 to 17. As in the case of a DC voltmeter, the rectifier voltmeter circuit in Figure 3 to 17 uses a series connected multiplier resistor to limit the current flow through the Pmmc instrument. The meter deflection is proportional to the average current, which is 0.637 x peak current. The actual current, or voltage, to be indicated in AC measurements is normally the RMS quantity, which is 0.707 of the peak value, or 1.11 times the average value. Since there are direct relationships between MMS, peak, and average values, the meter scale can be calibrated to indicate RMS volts. PIPO. A rectifier voltmeter as discussed above is for use only on pure sine wave voltages. When other than pure sine waves are applied, the voltmeter will not indicate the RMS voltage. V. pp. Pmmc VIMS OE \/ Instrument VAY. Figure 3 to 17. An AC voltmeter may be constructed of a Pmmc instrument, a multiplier resistor, and a full-wave bridge rectifier. The instrument scale is correct only for pure sine waves. Degree 52. Electromechanical Instruments Chap. 3W328. A Pmmc instrument with FSD equals 101A and R equals 1 kis to be employed as an AC voltmeter with FSD equals 100 V, RMS. Silicon diodes are used in the bridge rectifier circuit of Figure 3 to 17. Calculate the multiplier resistance value required. Solution at FSD, the average current flowing through the PMMC instrument is I equals 100 Pa. Ti underscore 100 Pa underscore 06370.037. BA. L equals, applied peak voltage, rectifier volt drop. Total circuit resistance. Peak current I, equals. Rectifier volt drops equals 2V, for D and D, or DZ and DS. Applied peak voltage equals 1.414 Vs. Total circuit resistance equals R plus Re. 1.414 Vms 2VE. NMR plus RM. 1.414 Vms 2V. Re equals Re. M. 414x 100V, 2x 0.7, underscore. 157 Pa IKA. Equals 890.7 knots. Example 3 to 9. Calculate the pointer indications for the voltmeter in example 3 to 8, when the RMS input voltage is A, 75V and B, 50V. Solution. A, TOI equals 0.63715 equals 0.637, 1.414 Vs R plus R, equals 2. 890.7 knots plus 1 kd. Equals 0631, 1.414 x 75V, 2.x 0.7V. Equals 75 WA equals 0.75 FSD. Seconds. 3 to 5 rectifier voltmeter 53 underscore 1.414 x 50V, 2x 07V. W equals 0.637 F 890.7 knots plus 1 KO. Equals 50 NA equals 0.5 FSD. Example 3 to 10. Calculate the sensitivity of the voltmeter in example 3 to 8. Solution. In equals 157 Pa. FEMA equals 0.70 equals 0.707 x 157 Pa. Equals 111 Pa, at FSD. VEMS equals 100 V, at FSD. 1 AR equals TT 100 NAV 7 900.9 KO. CIVI. R. 900.9 knots. Sensitivity equals VV equals 2E. Equals 9.009 kV. Equals 9K. Examples 3 to 8 and 3 to 9 demonstrate that the rectifier voltmeter designed to indicate 100 V RMS at full scale also indicates 0.75 FSD when 75 V ms is applied, and 0.5 FSD for 50 V RMS. Therefore, the instrument has a linear scale. At low levels of input voltage, the rectifier current is also low, and this can result in errors due to variations in the diode voltage drop. The effect can be countered by using a shunt resistor across the meter, as discussed next for a half-wave rectifier voltmeter. Half-wave rectifier voltmeter. Half-wave rectification IG employed in the AC voltmeter circuit shown in figure 3 to 18. RSY. Shunting the meter is included to cause a relatively large current to flow through diode D. Positive half slices with intervening spaces, as illustrated. In half-wave rectification, Li equals 0.5, 0.637/, This must be taken into account in the circuit design calculations. 54/Electromechanical Instruments Chap. 3 Instrument. D. *PMMC BR. Figure 3 to 18 half-wave rectification may be used with a PMMC instrument and a multiplier resistor for AC voltage measurements. A shunt resistor, RGQ4, is included to ensure a satisfactory rectifier. Forward current level. The additional rectifier, D, minimizes reverse leakage current through D. Example 3 to 11. A PMMC instrument with FSD equals 50A and R equals 1702 is used in the half-wave rectifier voltmeter circuit illustrated in figure 3 to 18. The silicon diode, D, must have a minimum, peak, forward current of 100 Pa when the measured voltage is 20% of FSD. The voltmeter is to indicate 50 VRMS at full scale. Calculate the values of R and RSY. Solution at FSD, IQ, equals 50 WA. Meter peak current. I 50 Pa. Ln equals a 05x0637 equals 05x0637, smiley face, ha. At 20% of FSD, diode peak current 1, must be at least 100 WA, therefore, at 100% of FSD. 100%. FR cent pesc, equals 0% asterisk 104A equals 500 Pa. TR cent peak, equals DM plus Is. Stick peak, equals TM peak, LM. Equals 500 BA 157 Pa equals 343 Pa. Ven, peak, equals Linry equals 157 Pa x 1700.2. Equals 266.9 MV. Roy equals Vinpisk, equals 266.9 MV equals 7728.2. $4 Isen Pesky, 343 BA. Applied peak voltage, Verpeaks, VR. Fe, P equals S. A 1.414 Vangvini Piri SVF. Seconds. 3 to 5 rectifier voltmeter. 55 R equals 1.414 VS Vini Pete, PEVP. L FIPIC equals 1.414 XEY 50 V, 600.9 266.9 MV MV-0.7 V 0.7 V. 500 Pa equals 139.5 K0. Half bridge full wave rectifier voltmeter. The circuit in figure 3 to 19 is that of an AC voltmeter employing a half bridge full wave rectifier circuit. The half bridge name is applied because 2 diodes and 2 resistors are employed instead of the 4 diodes used in a full wave bridge rectifier. This circuit passes full wave rectified current through the meter, but as in the circuit of figure 3 to 18, some of the current bypasses the meter. During the positive half cycle of the input, diode D is forward biased and D is reverse biased. Current flows from terminal through D, and the meter, positive to negative, and then through R, to terminal 2. But R is in parallel with the meter and R, which are connected in series. Therefore, much of the current flowing in D passes through R, while only part of it flows through the meter and R. During the negative half cycle of the input, D is forward biased and D is reverse biased. Current now flows from terminal 2 through R, and the meter, and through D, to terminal 1. Now, Re is in parallel with the series connected meter and R. Once again, much of the diode current bypasses the meter by flowing through 3. This arrangement forces the diodes to operate beyond the knee of their characteristics and helps to compensate for differences that might occur in the characteristics of D and dy.